Well, we can have more questions afterwards. So I'm the chair of the ITER Council, as has been said, but I'm relatively new to fusion, and in my life I've been Director General of CERN, so the Large Hadron Collider, which you probably heard, that's my project, my baby. It's not too healthy at the moment, but it's coming back into health. Now, you people have joined fusion, so I think you know why fusion is important. It was implicit in your question. So I'm not going to tell you again why fusion is important, but I'd like to tell you the answer I give people. You must get your friends asking you, why is it important? Why is it always 40 years ahead, and so on. So I will give you the answers that I give to those questions. So first of all, to tell people that it's important, I explain that to make the deuterium and tritium are the fuels. Deuterium comes from water, tritium we make from lithium. Then I've done the following calculation. If you take the lithium in one laptop battery and you use it as fuel in the fusion power station, allowing for all the thermodynamic inefficiencies, etc., the amount of power to go back to operate the heating systems, etc., how much energy can you get from the lithium in one laptop battery? And the answer is 200,000 kilowatt hours. This is a lot of electricity. In Europe, that's the total electricity production, not just personal, it might be used by industry, street lighting, etc. It's the total electricity production per person in Europe for 30 years. So the lithium in one laptop battery will support the life, as far as electricity is concerned, of one European for 30 years. And I think people are very astonished by this fact, but it's correct, if we can make fusion work. And when you realize also that there's lots of lithium and you need so little, even it's economic to get it from seawater, we have enough for millions of years. So I say to people, I'm not certain that fusion will work, although I'm optimistic, but just look at it. We have enough fuel with no greenhouse gases for millions of years out there. So we absolutely have to try. But then they say, yes, but your predecessors said that, and they said in 40 years they have fusion, 40 years pass, you still say 40 years. So will it always be 40 years? Why is it 40 years? And the answer is, it's very difficult. First of all, you know that, I know that. But technology moves on and we are making progress. The second reason is that it's a matter of scale. And you probably know this, but if you take JET, for example, and you go to ITER, ITER is twice as big in every dimension. So the volume is 8 times. So with the same plasma conditions, you have 8 times the stored energy. But you've only got 4 times the area for the energy to leak out, and the heat has to travel twice as far on average. So simply going from JET to ITER, a factor of 2 in size, you gain a factor of 4. But it's better than that, because first of all we hope to have a better plasma, but we can make a bigger current, a stronger magnetic field. So the difficulty we have with fusion is you cannot demonstrate fusion on a small scale. If you wanted to convince people of coal power, you could make a coal power station as big as my hand. You can't do that. You have to spend billions. If you could do it cheaply, somebody would have tried to do it years ago. But it costs a lot of money even to do the proof of principle, which is ITER. And therefore, each step has been taken very cautiously. Society is not prepared to give you billions or billions until you're almost sure it will work. So that's made it very slow. The second reason, or the third reason, is that there's been no feeling of urgency and that money has been inadequate. I look back recently at a study made by the Americans in 1975 or 76, in which they said, if you give us adequate money, and they said, this is the budget we need, then we will have fusion, let's say, 40 years. But they said, if the budget is 20% below that, it's 50 years. If it's 30% below, it's 60 years. And below a certain level, we never get there. So everybody remembers the 40 years. But they forget that in fact the budget has been below the level at which you never get there. So society now, and this was more natural in the 80s, people were happy to burn coal forever, they thought it'd be there forever, and so on. Now we know better. We really have to get on and make it work. So then they ask, okay, so how long will it be? And that calculation is rather easy. It will take about 10 years to build ITER. Then we have to get DT. If we have adequate funding, and we have to remind people, this is an assumption. So don't believe the answer if the assumption's not right. If we have adequate funding, we develop materials, heating systems, remote handling technology in parallel. Then after 10 years of operation of ITER, with a few years of DT, we should have a design for demo and be ready to build it, if ITER works. And then that's 10 years, so it is 30 years, and that's only prototypes. So it's still 40 years, I'm afraid. But that depends on the assumption, but we can do it, and we must do it. Then they say, your question, isn't it very expensive? The fact is, the world is spending every year on energy something like $5 trillion. On this scale, fusion R&D is not visible. And it's not visible on the scale of the consequences for humanity if we fail to produce new energy sources or enlarge those we've got. Fission, vital, more solar energy, etc. But fusion can be an important point. So yes, it may be expensive, but it's not expensive on the scale of the turnover of the energy market, and the funding is absolutely needed. Well, then you get the question, won't it be too late? And the answer is, as far as global warming is concerned, more or less everything is too late. We should have started years ago. And in fact, personally, I cannot imagine that we won't burn the remaining coal, oil, gas on a time that is short compared to the time that carbon dioxide stays in the atmosphere, which is getting on for 1,000 years. So therefore, as far as climate change is concerned, I believe it's absolutely vital that we find out whether we can capture and bury the carbon underground. It's probably possible. It will put up a cost, however, so there's huge political challenges. But it's not been demonstrated on a large scale. On the other hand, as far as the even bigger challenge of what will happen when coal, oil and gas run out, fusion will be probably there in time. The fact is that we're getting near the peak of oil production in the world. Gas, a bit longer. You will read in the literature, if you just want energy, don't worry about carbon dioxide. Don't worry, there's enough coal for 200 years. But the next line says, at current use. Coal use is going up 4.5% at the moment. You people know about exponentials. 200 years of current use turns into 50 years with a 4.5% growth when you do the calculation. That's not very long. Maybe there's more, maybe there's less of coal. But on the other hand, when oil runs out, the first thing people will be doing is turning coal into oil. So that 4.5% may increase. So no, fusion will not be too late. It may be just there in time. Lev Aksimovich, the father of fusion research, was asked, when will fusion be available? And he said, fusion will be available when society needs it. And it turns out, if you, the young generation, can make the timetable that I was talking about, not when society needs it for climate change, that was yesterday. But it will be there, I hope, when we need it for dealing with the end of fossil fuels. So those are the answers I give when I'm having a drink in the bar and people, or talking to politicians, and they ask these questions.